Right, so as already mentioned, we are going to do the last cousin of the transforms for this course. Transforms और भी हैं, right? But by and large, these are the major three being used in engineering applications and maths and physics. And the first one we have already done is the Z transform, which applied to DT LTI systems, where the idea was that the complex exponentials are the eigenfunctions of DT-LTI systems, right? So using that idea and connecting it with what? The eigenfunctions, eigenvalues, right? We were able to suggest that, okay, we will try to write any given signal, let's say xn, as a linear combination of these eigenfunctions. That's the whole idea of the Z transform. Now, in case of Laplace, this was converted to the continuous time LTI systems, and there this complex exponential, right? This is a complex exponential in discrete time. This is a complex exponential in continuous time. We notice that this complex exponential was the eigenfunction. So from there the idea came out that, okay, then we can have a Laplace transform of continuous time LTI system. Similarity kitni zyada hai, it's all the same. Yeah, only thing is summation here because of discrete time, integral here because of continuous time, right? So now why we have discussed that in great detail, why we do that. But one thing was, what was Z here? It was any complex number a plus j b, right? What was S here? Any complex number that conventionally we write as sigma plus j omega. You could still write it as a plus jb, doesn't matter. Yeah, but conventionally, but notice the form, they're both complex numbers. Here S is the complex number, here Z, the base, yeah, is the complex number a plus jb. Now I gave you a hint of the Fourier transform when I covered Laplace. Yeah, the hint was that the Fourier transform is a subset of the Laplace transform. So that is what we are going to be looking at today, non-mathematically. Today we will not see, after this we will not see any equations. I want you to get a non-mathematical feeling of transforms, and I have developed it, your transforms, in the sense of eigenfunctions and all that story, but there is another way of looking at them, purely in the form of rewriting signals as sinusoids. So today we will look at that perspective, okay? But to get there or connect to the maths, we will do that afterwards also. But as I have mentioned already, this is your set of complex exponentials in time domain, yeah, where S is sigma plus j omega. Yeah. Now if you expand this, the real, if you look at just the real part or the imaginary part, what does that look like? We have done that before. Okay, those are basically, what are they? They are sinusoids that may be decaying. Okay, what determines the frequency of those sinusoids? The complex part, imaginary part of S. What determines if they are decaying or growing? This guy. If it's positive, they are growing. So this is positive, it is growing. Okay. If it's negative, it is decaying. This is the whole set. Now you can imagine how many you can create. Draw to many cast, you can have so many different frequencies. You can have so many different levels of decay or growth, right? So there could be something that is extremely fastly changing and then extremely fastly decaying also, yeah, because of this extremely fast decay factor. So bahut sare, you can make a huge pool of these. Yeah. Now within that pool, there is a special group whose magnitude neither grows nor decays. वो भी allowed है ना, इसके अंदर ही है ना, sigma की value 0 रख दें. Okay, then you are at neither growing. What can you play with that now? Only
complex part.
omega,
Yes.
right? What is that reflecting here as? Frequency, time period, or the inverse of that frequency. उसको बढ़ाएंगे frequency को तो fast variation हो जाएगी, कम करेंगे तो slow हो जाएगी, but the amplitude is not going to change. Yeah, that is also within this class, but that class alone itself, where we say that sigma will be set to 0, we call them pure sinusoids. Okay, why pure? In the sense that they are neither decaying nor growing. They look exactly like sinusoid. जो एक आपने आदत बनाई, cost बनाते हैं ना, आप draw करते हैं, sine draw करते हैं. You can play with the phase also later, but for now we are mostly looking at the decay or growth. If you restrict yourself to this set, then you are restricting yourself to what? E j omega t. ऐसे ही है ना? Why is that? Because you can see that this is E sigma t times E j omega t. If sigma is 0, E0 is 1, you are left with just this term. Right? That is E j omega t. And if you restrict yourself to these eigenfunctions, then you are working with a subset of the Laplace transform, which we call the Fourier transform. Okay, इनकी developmental history different है, but finally they end up like this. ये इनकी तरतीब बनती है. ठीक? So and by and far in engineering today, Fourier is the dominant transform. Okay, इसके बाद most likely you will not see Laplace and Z as often as you will see Fourier. Zikr may be discrete Fourier transform, fast Fourier transform, millions of variations, but in general it's the Fourier transform that we say has in a way transformed modern engineering. Okay? Without it, आपको अभी तो शायद समझ नहीं आएगी, लेकिन इसके बगैर we would be far behind in progress. Okay? It has transformed the modern engineering. Digital जो signal processing और जिस पे फिर ये सारा कुछ आज की devices based हैं, all of them, they will take this signal, convert to Fourier, work with the Fourier, convert it back, and then give you the results. Right? So that is why I am going to dedicate the last remaining lectures जो भी हैं हमारे पास अभी to basically this guy. Okay, conceptually you have already learned the background, right? Eigenfunctions का सारा कुछ आप कर चुके हैं. Then you have seen the Z and the Laplace transform. You have seen their inverse. इसका भी वैसे ही होता है. क्यों वैसे होता है? Because this is a subset of the Laplace. So when you were working with Laplace, when you are doing Laplace transform or inverse Laplace transform, you were also including this part, right? So there is conceptually, or say in terms of doing inverse Laplace or inverse Fourier, वही है partial fraction expansion, nothing new. Okay, so nothing to be scared of in that sense. But what you need to be able to see now, I want you to look at signals and see what does it really mean for this signal to have its Fourier transform. Okay, what is that going to look like? So we leave this behind now, right? ये pool आप ज़हन में रखें, this will come back, the pool or the sub pool, okay, of sinusoids. But then what we do with that, let's look at that very graphically today. I think there are no more equations in the lecture. Let's see, hopefully it will continue recording. If it doesn't, then we just of course I can send you the slides. Slideshow. Right. Any of you into English literature? Eh? The writers, directors, they are supposed to be into these things, na? No, a drama is a literature, isn't it? Yeah. अब तो वो सिंगर को भी नोबेल प्राइज मिल चुका है लिटरेचर में, राइट? किस सिंगर को मिला है? विकेट। किसको? नहीं नहीं, ये I'm talking about Nobel Prize in Literature. Yes sir. चेक करें जाके, अमेरिकन सिंगर है, कंट्री म्यूजिक गाता है, बड़ा मशहूर है. His songs reflect a lot about human emotions, life and those things. तो उसको literature का Nobel. So anyway, if you read books, especially old English, you would know what is a specter. क्या होता है? स्पेक्ट्रम तो आपको पता है, उसमें वो निकला है लव स्पेक्टर से. व्हाट इज स्पेक्टर? SPECTRE.
जेम्स बॉन्ड मूवी.
या वो भी है. वो क्या था स्पेक्टर?
Different colors of different people.
Right. Specter in English means ghost, an invisible thing. ठीक है? Specter is the proper English word or an old English word for ghost. ठीक है? Now it's mostly used literary senses या जैसे movies वगैरह में the specter of this, यानी उसका ghost आपके पीछे लगा हुआ है किसी चीज का, right? So specter is ghost and spectrum basically is the ghosts in your signal. So why do we call this spectrum spectrum? Yeah? When we observe, आपको when you look at the light itself, yeah, there are colors hiding inside it. Okay, if you put a prism in front of it or in its path, those ghosts become visible. तो उन ghosts की जमा को हम क्या कह देते हैं? स्पेक्ट्रा या स्पेक्ट्रम. ये स्पेक्ट्रा जमा है इसकी स्पेक्टर की. और the ghosts in your signal is literally that meaning. Okay, the invisible things in your signal, or in this case the invisible colors in the light which were previously invisible. Yeah. So why am I bringing this up? Because we talk about Fourier spectrum, Laplace spectrum, all that. In transform domain we talk about spectrum. Yeah. So today we will see what that spectrum is. Let's see. Do any of you know what is sonar?
Yes,
So I think I forgot to change it to this side. Let's see if it is still recording. Yes, it is.
Yes sir.
तो स्क्रीन रिकॉर्ड कर ले.
हाँ वो भी है लेकिन ये कर लेंगे. So as I mentioned, the spectra part you have seen now. Yes. Sonar. Anybody can tell me what is a sonar?
The signals are pulsated at a given object and they're reflected and the distance
So what
between
does a
them is
radar do then?
Sir, radiation.
Okay, what's the difference?
different frequency
Sir,
of waves.
ultrasonic sound signals.
Yes. Frequencies तो radar भी है different use करता है. Radar uses electromagnetic waves to do what you said. Throw something and collect the reflected. Sonar does this with sound. पानी में sound is better to work with. Yeah. So sonar does that. Now this is one kind of a sonar equipment. They drop it into the ocean and it records sound waves coming from different directions. There is active sonar and passive sonar. Suppose you are on a mission and you have dropped this and you have recorded a signal. This is your time domain signal that the sonar gave you. Okay. Now what can you see in this signal?
Noise.
So variable magnitude.
Okay, variable magnitude. What else?
Sir, decaying, growing.
Some decay, right? Some amount of periodicity,
Yes.
right? प्योर नॉइज तो नहीं लग रहा वो तो.
नहीं सर वो
There is some amount of periodicity, but that's the thing. A lot of time domain signals, apart from the very nice sine and cosine, जो real life में बहुत rarely नजर आते हैं, the real signals you will collect almost always will be this confusing. क्या करेंगे इसका? थोड़ा सा देर बता देंगे कि इसका what's the magnitude? That's it. क्या बताएं? जब थोड़े बहुत कुछ little bit periodicity. Time domain is not very conducive to analysis of the components of a signal in general. That's where the power of Fourier transform or the transform domain comes. Okay, so you and I are confused. If we ask this guy, कौन है ये?
पहले कंफ्यूज लगा नाम लिखा हो सर
जिस दौर में वो रहता था ना, आप भी कंफ्यूज हो रहे थे. ना बिजली थी ना घर में पानी उसका सही था. राइट. सो कौन है? नाम लिखा हुआ है, मेरा लिखा हुआ है नीचे.
नहीं सर वो उसके बाद में मेरा
दैट्स द पर्सन हु टुक द पेंटिंग और गैस ही कर ले, कॉन्टेक्स्ट से भी गैस कर
मैं
लेते
तो जोड़
हैं. फ्रॉम द कॉन्टेक्स्ट, today's context, can you judge? Fourier. Okay, guess he can. Yeah, this is Fourier, and this guy was not working on solving your issues. Okay, I don't remember, but it's at least 150 years or 200 years ago. Yeah, he was not trying to solve our issues. उस वक्त तो electrical कुछ था ही नहीं ना. Yeah. They were given a challenge: how does heat flow through solid slabs? Heat है, solid material है, उसमें से कैसे travel करेगी? And while trying to solve that, he came up with a new mathematical approach that ended up becoming the Fourier transform. And his paper or his solution, there was an award related to that, some cash or some prize at that time. The big mathematicians of that time, including, if I'm not forgetting, Lagrange, you know Lagrange multiplier. Those guys were the judges of the papers or the solutions that came in, and his work was rejected by them. Okay, so but he fought back, and eventually they had to accept that what he was saying. They had some other theoretical issues with his solution, which we will see at some point. It relates to approximation. Mathematicians of that time hated the word approximation. There is nope, either it's this or it's that. But he ended up solving with the approximations, and he then showed them that that is the future. Anyway, so if we ask this guy, what does he see? Basically, if we take the Fourier transform, in that signal he sees in the frequency domain. He's not looking at the signal in time and amplitude. That's what we record. Yeah, he takes it into a different domain. Okay, याद है जब मैं ट्रांसफॉर्म पढ़ाया था, I mentioned your favorite show, fourth season जिसका आया अभी या fifth आया क्या है वो, Stranger Things. There is the upside down, right? So he takes it into another universe, completely different universe. In that universe, the x-axis is not time, it's frequency. What frequencies are there in this signal? And the y-axis shows you if it is 0, that means that frequency is not there in that signal. If it is very high, that means that frequency is very strong and powerful in there.
And what does this frequency represent in sonar?
Yeah, we will look at this now. Yeah. For now, it's representing that this signal is made up of what frequencies? These frequencies, and let's see. I had a pointer. मैंने pointer एक लाया था ना, आप लोगों को कहाँ गया? Anyway, maybe I can use the. Oh yeah, here we go. Okay. So it's telling you what frequencies are there in the original signal, which means okay, if there is a peak here, This is where is the peak at 13 hertz. So 13 hertz is among the dominant frequencies in there. Yeah. Then there is another peak at 26 hertz, 39 hertz, and another peak at 60 hertz. Then there are some non-descriptive peaks or say contributions here, and then the contribution drops off. There is no more signal or no more frequencies after 80 hertz in that signal. There could be reasons for that, but what you need to focus on then is what? Okay, what is this component? What is this? What is this? What are these peaks? Why are these the dominant frequencies? आपको इसके अंदर you could see some periodicities, but because it's such a mixture of frequencies that you couldn't really tell, right? कि 13 hertz है क्या है? Now you know that if you take all these frequencies together, these dominant ones, you will get a major chunk of this because they are the dominant ones. बाकियों का amplitudes तो both relatively low है. Okay, so they may be the noise part. We can argue. वो फिर हम देखेंगे. Again, the power of the frequency domain. You're analyzing the ingredients, sources of the signal. Yeah. Now, spectrum. This is the spectrum. Yeah. So it was hidden in here, but now you put the prism of Fourier transform, and you got this ghosts in there. There they are. कार्टून्स में भी घोस्ट ने वो शीट पहनी होती है ना, ऐसी शेप होती है उनकी. अगर इसकी हम आंखें बना दें ना इधर एक दो तो राइट. सो these are the ghosts here, and now what are these ghosts telling us? Firstly, they're telling us, okay, we are the dominant. Yes, there are other frequencies contributing to make that mixed up signal, but we are the dominant ones. So we should focus on, okay, I put my sonar in there and I got a signal and there was these dominant frequencies. Who's making them? Source kya hai? Right? Why do I get these? Now, those who work with marine sciences and in the Navy know that a lot of submarines, okay, when their propeller moves, they create एक खास स्पीड पे उनका प्रोपेलर मूव करता है जब वो स्टिल हुई होती हैं, बस हल्का हल्का अपने आप को रखना चाहती हैं, राइट. दिस 13 हर्ट्ज corresponds to the rotation of the propeller. Okay, and propeller में तीन होते हैं parts, so you get overtones also. Okay, in the signal. कभी fan, if you look at the fan for long, क्या होता है? Still भी नजर आता है. Then sometimes you see it in three different frequencies नजर आ रही थी. कभी नोट किया? कभी full नजर आती है, कभी वो ऐसे लगता है कि एक slower वाली आ गई है, कभी still नजर आता है. Why is that happening? वो उसके तीन wings है ना, तो वो उसकी overtones भी आपको थोड़ी सी नजर आती है. Right. So you already know now. Okay, there is a submarine here. I need to be careful. Yeah. Now, why is there a submarine here and which part of the world is it from? Now, what's this 60 hertz? Yeah, good guess. हो सकता है, लेकिन अगर let's say आपने you collect the signal again and again, 2-3 मिनट तक और हर दफा आ रहा हो तो काफी शोर मचाने वाली वेव होगी जो could be. But let's say it's persistently there, then can you rule out the whale or something? क्योंकि वो तो एक बार बोल के चुप हो जाएगी, right? So what's going on? 60 hertz. Where have you heard 60 hertz?
AC voltage जो आती है.
Voltage, right? पाकिस्तान में कितनी है? 50, right? If I recall correctly, Europe also uses 50 and the US uses 60. Okay, so if you are now the Russian guys collecting the signal, you should be very worried. There is a submarine. अब वो जो submarine के अंदर जो current run हो रहा होता है ना, उसकी भी हल्की सी vibration पानी में जा रही है, ठीक है? That is creating this 60 hertz. So you know this submarine is running on 60 hertz AC system. So depending on which part of the world you are, you should be worried or happy that it's an ally or an enemy. Yeah. जाहिर है Navy doesn't just rely on this. Yeah, there are other things also. But already, just from this basic passive sonar, ये active भी नहीं है. There is another thing, active sonar, but it's just listening. Okay? Even a passive sonar is able to tell you a lot about what's going on in the water. And they not just this, they also use it to study calls of the whales and other fish. So let's see. Question? Right. So this is the question that ends up being answered by Fourier, although he didn't start like that. Yeah, but now this is what happens. Can we write signals as sum of frequencies or periodic functions? Okay. When we write it like this, we are saying that if you take a sinusoid of this frequency, of this, and this, and add them up, you will come very close to this thing, very close. Okay. Why not exactly? Because it's not saying there are only 3-4 frequencies. It's also saying these are there. It's also saying there's some sort of this trailing thing which later we identify through studies that it's a special kind of noise called 1/f noise. जैसे आपको होता है नहीं thermal noise वगैरह सुना होगा. This is a special kind of noise. So because you won't be adding those, if you add those also, all of them, you will get back this signal in time domain. Okay. So the question now, this is the question that the Fourier transform ends up answering or doing. Can we write signals as sum of periodic functions or frequencies? ये जो आप कह रहे थे ये periodic functions थे ना? Periodic है या नहीं है? Right? Decay है but still periodic. In Laplace they are periodic in the sense that they are repeating, but yeah, there is decay. In Fourier they are exactly periodic, right? क्योंकि वो ना decay कर रहे ना grow कर रहे. So whatever you get here, you get here, you get here, same value to keep repeating, right? So they are purely periodic functions. So that is the question Fourier answers. It tries to write every signal as a sum of sinusoids. What does that mean now? Let's look at it. It says, okay, in the time domain, I have this signal. याद देखा अभी जो हमने time में. What is that? This axis is time and this is frequency. Fourier asks, okay, in my bag or in my arsenal, I have only pure sinusoids. The only thing I can play with is their phase and their frequency. You could also play with their amplitude decaying, but then you will be working with Laplace transform. And Fourier, you are not allowing that, right? Only pure frequencies. So in pure frequencies, this is all you have. ये मैंने चंद ड्रॉ किए हैं, right? You could make many more. Frequency और बढ़ाते जाएं और कम करते जाएं. Yes?
उस signals में से signal के components हैं.
अभी बनाए नहीं हमने. But what we are saying is, I want to write this signal in terms of a pool of sinusoids, eigenfunctions, basically. Right? ये eigenfunctions and not just these. ये तो एक drawing है ना, इसमें आप फिर mathematically तो any omega, right? You ask yourself which ones of these I need and how much. That will be the eigen value. So already mathematically we have done that, but today it's just, so let's look at it. Let's any of you into baking करते हैं, interest है नहीं या ना आप लिटरेचर करते हैं ना आप बेकिंग करते हैं ना आप साइंस करते क्या है ब्राउनी आती गुड मुझे भी नहीं आती अच्छा राइट माइक्रोवेव में चीजें रखना बेकिंग नहीं कहलाता होगे पुटिंग थिंग्स इन माइक्रोवेव इज नॉट बेकिंग ओवन में अच्छा राइट सो लेट्स बेक अ Fourier cake today yeah so you are going to make a Fourier cake. What you're given जब आप बेकिंग शुरू करते हैं तो आपके ज़हन में गोल होता है ब्राउनी बनानी है पाए बनाना है केक राइट यू हैव अ गोल इन योर माइंड व्हाट्स योर गोल गिवन क्या है यू वांट टू गेट अ स्पेशल सिग्नल शेप व्हिच इज इन time domain. Maybe you want your cake to look like this. It's going to be a very ugly brownie, but anyway, right? Yeah. Ingredients क्या है आप पास? When you're going to make your brownie, you write down your ingredients. Sugar होगी, milk होगा, flour होगा, और क्या होगा? कोई flavors होंगे, कोई और इस तरह के oils होंगे, कुछ छोटे मोटे, yeah? Here you are restricted. What? You can only use sinusoids. They should not be decaying, they should not be growing. They can be sinusoids. The only thing you can play with is their frequency. Okay? How much you use, that is playing with their amplitude. But that, but otherwise, the only ingredient you have, अब सोचें हाली कोको पाउडर से ब्राउनी तो नहीं बनने लगी लेकिन बहरहाल दिस इज व्हाट वी डू हियर कोको पाउडर का है मैंने उसकी राइट अच्छा राइट सो चूज अब आपके पास चॉइस क्या है हाउ मच ऑफ ईच इंग्रेडिएंट हाउ मच मीनिंग व्हाट एम्पलीट्यूड कितना आप डाल सकते हो राइट और कौन से यूज करनी है आपने फ्रीक्वेंसी दैट्स ऑल यू कैन चूज So let's see. This is the brownie you want to make. ये कर्सर यहाँ इसकी वजह से रुका हुआ है?
No sir.
किस वजह से?
Picture में
वीडियो है ये
नहीं अच्छा गायब हो गया है वो इंतजार कर रहा था कि हम उसका जिक्र करें
वापस आ
This is a gift or something.
Right. So let's say this is the brownie you want to make. This is the cake you want to make. This is your signal that you observe in time domain. अब ये बहुत टेढ़ा मेढ़ा लग रहा है. You're not able to identify यार इसमें noise क्या है, इसमें इसके ingredients क्या है, कहाँ से क्या है. What are the frequencies that made this signal, right? So you go to your Fourier baking box and you look at the ingredients. What do you have there? Only कुछ और नहीं डाल सकते. Otherwise, you're not making a Fourier cake. You're making something else. Yeah. So you say, okay, to make this shape, I need 3 sinusoids. Okay. The first sinusoid will have frequency this much. The second will have more than that, and exactly how much वो देखेंगे हम बाद. And the third one will have this much. The key thing is you end up concluding somehow वो अभी हम नहीं दिखा रहे आपको वो that's the mathematics yeah but you end up concluding that you need these 3 from your ingredient box these 3 sinusoids of 3 different frequencies and their amplitudes notice करें amplitude कम हो रहा है so you take more of this one slightly less of this one and even less of this one और ये अब time में है this is time this is frequency okay If you sum these 3 आप पता है क्या होगा अगर point wise sum करेंगे पता है क्या आएगा ये आएगा इसका हर point आता जाएगा amazing है ना क्या कितने वो smooth हैं
जैसे कि periodic चल रहे हैं लेकिन
right they're so smooth and nice and if you sum them up point wise you get this ugly guy kind of yeah so what happens now the story doesn't end here this is you have decided your ingredients now this looks very wasteful in terms of representing क्या अब आप हर दफ़ा ऐसे लिखेंगे इसको तेरी वो 3 sinusoids ड्रा करेंगे so being humans and especially in sciences and mathematics we try to write the most summarized version of things उसी के लिए tables होते हैं graphs होते हैं formulas होते हैं right that is what we do So we say, okay, this is not very efficient. It shows you conceptually what happens, but then why not maybe put this in a table? Ingredients का लिखा होता है ना आपके वो इतना ये डाले इतना ये डाले इतना ये डाले ऐसे ही ना तो you say, okay, I make an ingredient table तो तरकीब होती है so sinusoids तो हमें पता है 3 चाहिए I need 3 फर्स्ट विल बी 1.5 इनकी जो वेट है और इनकी फ्रीक्वेंसीज ये होंगी मैंने एक्चुअल वैल्यूज यहाँ नहीं लिखी हुई अभी बट यू विल राइट हियर व्हेन यू मेक योर ओन केक दैट दिस इज मे बी 50 हर्ट्ज दिस इज 100 हर्ट्ज दिस इज 150 हर्ट्ज हाउ यू फाइंड दैट अगेन दैट्स द मैथमेटिक्स फॉरियर ट्रांसफॉर्म बताया करेगा आपको लेकिन conceptually this is what's happening. Now the table is also very cumbersome, space ले रहा है, right? So what can we do? Conceptually we understand now what's going to happen, but can we represent this or this in a more compact way in a graph, so that we don't have to like write this whole thing? Okay, let's say I come up with a new kind of a graph. On the x-axis it's frequency, on the y-axis it's the scaling or the amplitude, how much I need. Then on the x-axis I scan the x-axis. If I need 5 Hertz, I put a line there. How big is the line? That will depend on the relative scaling or the amount of this guy I need. Then I go further, and if I need another frequency, yes, I need 10 Hertz, I put a line showing that I will need 10 Hertz also to make this cake. And how much of that will be there? 0.5. I go to the third one, 15 Hertz. How much I need? 0.25. This now is really a very nice and concise representation of what I want to do. So this is what you see when you take the Fourier transform. Okay, this graph, and this graph you should always look at it as your ingredient, as your tarkeeb jo hoti hai, baking method. Yeah, this is your formula for the baking of this cake, whatever that cake was. Yeah? So every Fourier transform graph is actually a formula for making the time domain big. Then we use that for analysis, wo sab apni jagah hai. Yeah, but if you understand this, then the analysis will make sense to you. So then what do we do from here on? Should we always go this way? Itni lambi kahani. Yeah, from here on we skip this middle guys. But it should be in your mind. Clarity aapko honi chahiye. ठीक है? From here on, in terms of working, we will skip this and we'll say, okay, this is time domain, this is its frequency. We skip the whole middle thing. Yeah, because that was not very, let's say, conceptually तो अच्छा था, but representation में it wasn't very efficient. So that's what I did here already. Time था, I showed you frequency, right? Frequency and amplitude. ये वही है ना formula.
Yes, sir.
It's telling you this is now how do you look at it. It's a cake you want to make, and this is the formula. You know the ingredients already. वो हमें जिक्र करेंगे, sinusoids, right? How much of those sinusoid? You need 13 Hertz, 26 Hertz, 39 Hertz, 60 Hertz. How much of each? This much of each, and you will get close to this thing. Okay. Any questions? No? Right. So, then I have a question for you. I want to make this cake. Okay. Draw me the baking method. Tarkeeb draw करके दे. याद है draw हमने किस बार करनी है? Frequency and amplitude. Yeah, that will be in the form of a graph, right? So what's the now I haven't given actual values here, so you will not be able to pinpoint the frequency, but कुछ तो आप general कोई frequency ले लें. Let's say this signal has a frequency f naught or something. Yeah, so 5 Hertz ले लें चले. 5 Hertz. First of all, tell me how many ingredients do you think you need? One. ये है ही वो खुद ही है. Right? Let's say this is 5 Hertz, so you need just to pick up that 5 Hertz from your ingredient box and set its scaling to 1. क्योंकि एक ही है तो relative scale उसका अपना ही होगा. So
ये impulse की बन जाएगी.
हाँ. Yes, a pure sinusoid in frequency in time becomes impulse in frequency. Yeah? Okay. So each of these, if you notice, has just one line. Yeah, ये था जो मैंने आपको दिया था, राइट? Its frequency is just you just need one frequency, जो भी है. अगर ये 10 hertz का है, from here you don't read frequency, right? You will read time period to invert that to get the frequency, and that is what you need here. और सिर्फ एक ही है तो वो उसी का बस जो भी relative amplitude उठाना. Now what happens if the frequency of this goes lower? क्या होता है आपके फॉर्मूले में? The bar moves to the left, right? क्यों? क्योंकि this is saying okay this was 5 hertz, now I have gone to, ये तो आप नजर आते हैं ना इनमें से frequency किसकी lower है, किसकी है lower? Left one has a lower frequency. So if this was 5 hertz, maybe you have gone to something much lower, maybe 1 hertz, and there is still one sinusoid. The ingredient is still one, but its frequency has changed. So what does this tell you? That when in one domain the frequency goes down, the peaks shift to the left in the other domain, right? Like upside down में मेरा कुछ होता था, लाइटें ऑन होती हैं क्या? Yeah. So that's the thing. What's the extreme version of frequency going down? DC, zero frequency. So देखिए peak कहाँ है?
Zero.
That is in conceptually that is still a sinusoid of zero frequency. So फिर zero पे एक line बनेगी, right? Now आपने जो कहा this in mathematical terms this is delta t exactly क्योंकि t zero पे है. This was basically delta t minus 1 or t minus 2, yeah? But this is delta t. आपको याद है हमने when we took the Fourier Laplace और Z transform of delta क्या आया था उसका? नहीं, हाँ 1 यानी constant आया था, right? And I told you there is duality. You have done an open-ended lab also. So in time, if there is a delta, it converts into a constant in frequency, and because of duality, it holds the other way also. If in time you have a constant, in frequency domain it becomes a delta. वही हो रहा है ना वो देखें, yeah, okay. It's this delta is here. This is duality also. Yeah, and you saw that mathematically and in the lab also. So what happens now? You start with the zero frequency. It is at 0. You start now increasing the frequency. It is still a delta, but what's happening to the delta? It's being shifted. By how much? By the amount of frequency. So it becomes delta f minus f naught, because the x-axis here is f, yeah, in the frequency domain. Okay. So some Fourier transform visuals. As frequency increases, the Fourier transform peaks move outwards. Okay, and if you have that idea of ingredients in your mind, this will make perfect sense to you. Yeah. Okay. What else? Again, I want to show you what I mentioned before. What really happens? You want to make this kind of cake. Yeah. You split it. You say, okay, this is the time. I like this kind of figures also. We just use them for teaching. Normally, फिर उसके बाद हम use नहीं करते. We just go to this last one. Yeah, but it's very, very instructive. Look at what's happening. Time domain ये है ना. This signal, can you see it where it is? It's on this axis. Yeah, ये ऐसे time amplitude. But what we did was we said, okay, to get this in time, what frequencies do we need? So we added a frequency axis. And we noticed or found somehow, दिखाया नहीं अभी ये, that actually Fourier transform mathematically tells us. Yeah. What we did here, we said we need a sinusoid of this frequency, one sinusoid of this, and one. And the first one, if it's omega naught, the second should be 5 times that, and the third should be 9 times that. And their amplitude should be relatively like this. And if you now add them point-wise, so one point here, 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 if you sum them up, you will get this point. So अगर आप उसको ऐसे sum up करते हैं, you get your original cake. Okay. So this is a very nice depiction of all that I have said. But then what you do again, you summarize this information into this formula. Yeah. इन्होंने ये लाइन लगा दी just to give you an envelope, but you don't have to do it. It can just be these 3 peaks. यही है ना आपका रिजल्ट, यही कह रहा है. To get this cake, to make this shape, you need frequency omega naught, 5 omega naught and 9 omega naught. And the relative amplitudes are, well, first one is maximum, second is reduced, third is further. कैसे वो reduce हो रहे हैं, क्यों हो रहे हैं, वो फिर Fourier transform जब हम लेते हैं, we get that value. Right. Again, same thing. This is your signal in time. You expand it in frequency, try to see which frequencies you will need to make this in time, and then you collect the information of each frequency on the frequency axis. Yeah. One more thing happening here, similar thing. Yeah, same thing, showing in different dimensions.
So इसकी कोई graphical interpretation तो नहीं है ना?
किस सेंस में?
Graphically तो नहीं करना होगा ना, mathematically सिर्फ Fourier.
You won't have to draw this 3D thing, but yes, there can be graphical in the sense that you are given, let's say, you are given this, and you are given this, and then you are given different plots, and you are asked, okay, A, B को match करें C, D के साथ, इस तरह का हो सकता है, right? But yeah, I won't ask you to draw this 3D thing, it's too hard, मैं भी नहीं कर सकता, it's not really, it's for understanding only. Again, another example, as I said, today's lecture is more graphical, everything. Another example, if you had this in time, this shape, yes, and you wanted to see, okay, what frequencies do I need to build this shape? Actually, you need these 4 frequencies, okay, and these are their amplitudes, 0.5, 0.5. If you add these frequencies, then you will get this shape. You can even get, अभी जो red है ना, the red one, that is your cake you want to build in time domain. Yeah. You can even build things that are very sharply changing, sudden drops on. Okay. When there are sharp changes in there, you need a lot of frequencies, but you can still try to approximate. Okay. So actually you will need infinite number of these frequencies to get the exact sawtooth. ये जो shape है ना, ये वाली. Sharp change is very hard to capture. So reality में भी ये होता नहीं है वैसे, लेकिन you can get close, and in the limiting terms you can get exactly that value, but it doesn't really matter. In a lot of what we do, the final bit is so weak and so low, it's usually coming from noise elements, so we don't really bother about that. Yeah, but this is just to show you. We will we'll look at this principle later, that when there are sharp changes in your signal in time domain, it normally means that you will need a lot of frequencies to create that cake. Okay? That's all woes mein. But you can still make them. Notice perfectly periodic sinusoid, yes, simple, this guy. Periodic, yes, but sharp changes, so you need several frequencies. Yeah, and actually it goes on. Ye score bhi chahiye. Actually, to get this, there is a theorem that proves that to get this infinitely sharp edge, you will need infinite number of frequencies. But like a geometric series, the value of those frequencies is going so low that उनका contribution बड़ा थोड़ा सा रह जाता है. Right? This is related to the kind of approximations that I mentioned that the mathematicians of Fourier time didn't really like. But so let's say this is your signal. You're scanning the frequency range and you're trying to see, okay, I need how many frequencies. So for some signals, you actually need a continuous range of frequencies within a band. ये कह रहा है कि आपको ये signal बनाने के लिए, to make that signal, this one, this red one, in frequency, what do you need? basically you need all the frequencies in this range but nothing outside it. ये लेकिन ये continuous आ गया ना, इससे पहले तक whatever we were looking at was more discrete, right? Separate frequencies चाहिए थी, लेकिन a lot of signals end up asking you for continuous band of say frequencies, right? So वो तो आप नहीं बना सकते, you can approximate. We will see that also.
So symbol क्या था वो वाला?
कौन सा?
Sir,
जो psi type है?
yes, sir, ये.
Yeah, some people use that for the frequency. We will use omega or f. Okay. So, right. Any questions so far?
सर ये स्क्वायर वेव जो है ये हमें बता रही है इसकी रेंज क्या है सिग्नल, मतलब इस विद इन दिस रेंज सिग्नल हमारा लाई करता है.
Within this range of frequencies,
Yes, sir.
right? These are the frequencies. This is what it's saying. It's saying that if you had a signal of this shape, जिसको हम sync function कहते हैं actually, in time, आपने record किया whatever this was time domain, its frequency domain is actually going to be some sort of square wave. Okay, what it's saying, this is frequency domain. Ingredients वाला idea आपको याद है? Okay. To get this shape, how much of frequency do I need from here? Zero. Zero है ना ये? How many frequencies I need? Let's say this is 5 hertz and this is minus 5 hertz and this is 5 hertz. Yeah. How many frequencies above 5 hertz do I need? Zero. क्योंकि उसका value zero दे रहा है. Do I need the frequencies between minus 5 and 5 hertz? Yes. Which ones? All of them. क्योंकि continuous आ रहा है. It's not saying take this one minus 4.5 or 4.5. It's not saying take these only. It's saying take them all. And then which of them dominate? None of them. सारों की बराबर values है, right? Otherwise, what you would have had, let's say you would say, okay, I need this one a bit more, this one. This would be a discrete case, yeah? वो भी आपने इससे पीछे देखी example. So there are all kinds of situations happening. Okay, वो कोई मसला नहीं. But again, when you look at it, think of it in the ingredients term, and then it will start making sense to you. So in summary, it's saying that this signal, the sync function, is actually made up of a continuous sum of frequencies of equal value within a certain range. That's all it's saying. Yeah? फिर उसको आपने बनाने के लिए क्या करेंगे वो हम देख सकते हैं. And the converse is also there, yeah. So if in time your signal looks like a square wave or just a square pulse, basically not a wave because it's not repeating, then in frequency, you know what it will look like? It always holds duality actually. Mathematically we can prove actually. So its frequency domain will be a sync function. Okay, so if in time it's square, frequency it's a sync. If in frequency in time it's sync, in frequency it's a square, or a rectangle. Right. So any questions so far? No. Now you should have a couple of questions really. Yeah. From this, क्या होने चाहिए आपके ज़हन में? क्या है? Integral क्या हो?
The question is
Integral. We discussed at the start. We did Laplace,
yes, sir.
right? We saw that EST was the eigenfunction. So we did Laplace. What was Laplace? XS was what?
X of t.
Right? So this is what the integral is needed for, to sum up the frequencies you have chosen. Now if those frequencies turn out to be continuous, you will need integral. If they turn out to be discrete, the integral will automatically reduce to summation. So वो उन्होंने एक general लिखा हुआ उसमें ना. Right, so this is the formula of the Fourier transform actually. Okay, except for ये थोड़ा सा complicated लिखा, we will stick to replacing this with j omega t, E minus j omega t. That's it. Yeah. So what else? What other questions you may have? Right. So again, always when somebody is telling you something, ask a couple of whys. Okay, you should always have a couple of whys. बहुत ज़्यादा whys पे आप जाएंगे तो फिर मसला हो जाता है, लेकिन शुरू में 2-3 why तो होने चाहिए आप पर, right? So one question you should have asked is it always possible to write signals? We are saying we are going to write signals and sum of sinusoids, yeah? But is it always possible? हम ऐसी क्लेम करने जा रहे हैं जो पॉसिबल ही ना हो, होता है अक्सर सिग्नल्स का फोरियर बनता ही ना हो, तो क्या फायदा उसका, right? So you should ask this question. I'll answer it briefly for you. No. अब अगला सवाल क्या होगा? क्यों करते हैं फिर भी हमारा आर बी क्रेजी, राइट? अगर है नहीं, yes, it still makes sense. Why? कोई पढ़ के जल्दी से बता सकते हैं? Why does it still make sense to work with Fourier transform?
All physically realizable signals have Fourier transform.
Yes. वो जो no है ना, that's in a theoretical world. Okay? वो जो theoretically आप कोई अजीब सा सिग्नल बना लें और उसका जब आप मैथ से करने लगें तो मैथ ब्रेक डाउन हो जाए. Yes, you can do that. But practical signals cannot be like that. होते नहीं है in reality. So मतलब this is known.
अभी तक चल रहा है.
हाँ. Yes. Actually, to get that thing, you will need something of a signal of kind of an infinite power. अब हमें पता है universe, the way it works. You work with geometric series, infinite numbers, but we know होते नहीं, right? क्योंकि वो energy expand हो जाती है, खत्म हो जाती है. So that's why we know कि वो होने नहीं लगा मसला. अच्छा, ये भी आपको पूछना चाहिए था. We said we are going to use periodic functions, right? So why these periodic functions? Yeah, why not non-periodic functions or anything else? जो ingredients थे हमारे वो sinusoids थे ना, periodic थे. तो क्यों हमने periodic क्यों लिए?
repetitive होंगे तो same outcome हर period के बाद आता रहेगा.
लेकिन signal हमारा
One answer, of course, you already know from here. We didn't start with periodic, but what we ended up with was finding the eigenfunctions, and they were sinusoids mostly. But there is another reason physically, is that a large number of physical phenomena have underlying periodicities. Physical signals or phenomena can often be identified by their characteristic frequencies. आप पेंडुलम पढ़ते हैं, सबसे पहले क्या निकालते हैं उसका? टाइम पीरियड. व्हाट्स दैट? फ्रीक्वेंसी. इन्वर्ट करें, कौन कैरेक्टराइज करता है उसको? फ्रीक्वेंसी. राइट. वाइब्रेशंस पढ़ते हैं, क्या निकालते हैं उसका? ऑसिलेशंस. क्या करते हैं हम सबसे पहले? टाइम पीरियड, फ्रीक्वेंसी. A lot of natural phenomena are actually based on periodic happenings. Underline, yeah. Flute है, म्यूजिक तो प्ले करता है ना कोई, आप वो भी नहीं, राइट? रिकॉर्डर है. यू कैन एक्चुअली डिस्टिंग्विश बिटवीन, अगर इनका आप टाइम में सिग्नल ड्रॉ करेंगे ना, तो अगर कोई अच्छा प्ले कर रहा है फ्लूट तो बड़ा स्मूथ सा कुछ प्यारा सा ऐसे कुछ बनेगा, या पर उसमें भी अजीब अजीब सी पीरियडिसिटीज मिक्स हो रही होंगी. बट इन फ्रीक्वेंसी इट्स वेरी क्लियर. You need these 4 frequencies of this much value, 436 Hz, 872 Hz. उनकी relative value इतनी हो, या आप कंप्यूटर पे जनरेट करें, उसको प्ले करें, आपको फ्लूट की आवाज़ आना शुरू हो जाएगी, right? After that, of course, you can play with the bass, treble, timbre, everything to create more, but the basic structure is here. इसलिए तो आप म्यूजिक सिंथेसाइज कर पाते हैं ना, वो बैठ के अंदर कुछ बजा तो नहीं पाता बंदा, yeah? So a lot of natural phenomena are based on periodic, not just music, our voice. Yes, our voice, when we say these sounds, उसमें बड़ी specific periodicities होती हैं, छोटी छोटी. Chemicals, when you study chemicals through different radiation techniques, they vibrate in response. Okay, those vibration, again vibration क्या होती है? Frequency. Yeah, so they vibrate in response, and the frequencies of the vibrations are unique to unique chemicals, or this is for communication, Vodafone, electromagnetic radiation. This is for identifying different chemicals by the vibrational. आप उनके ऊपर radio frequency फेंकते हैं, in response they vibrate. That vibrations और जो उसमें जितनी frequencies होंगी, that depends on. Let's say if you wanted to find TNT and you found vibrations of these frequencies, ये Fourier transform है हर एक का असल में, ये x-axis Fourier. अगर उसका Fourier transform इस तरह का आ रहा है तो इस chemical को side पे रख दे. TNT पता है ना क्या? Yes. एक कोई जो कोयटा TNT भी है इस्लामाबाद में, तेज चाय दे देते हैं उन्होंने TNT से चाय को इतनी तेज है वो के राइट. सो ये भी आपको पूछना चाहिए था. We said okay periodic, but periodic तो square wave भी हो सकती है ना.
वो हमने देख लिया कि वो साइनोसाइड को ही हमने
हाँ वो इधर से मैथमेटिकली इधर से आ गया. Now also look at
हार्मोनिक सप्लाई
पहले एक वजह they are smooth analytically. For sinusoids के integral derivative वगैरह आराम से निकलते हैं. इसका तो आप पागल हो जाएंगे. Okay, वो exist ही नहीं करता actually इस point पे. Derivative वगैरह. So also I like to I always try to see both sides, the practical side and the mathematical side. Yeah, practically also a lot of things are smooth sinusoids. ये क्या है? तो पूरी कायनात कवर हो रही है इसमें अक्सर. A lot of this reference a lot of mechanical behavior, vibrations, वो सारा जो आप machines में पढ़ते हैं चीजें. Yeah. What's that? ऊपर.
मैग्नेटिक.
Yes. What is that thing जो middle में plus minus हो रही है?
सर वो कम
Voltage.
सर मैग्नेटिक पोल नॉर्थ पोल साउथ पोल.
So that is antenna. पता है आपको antenna क्या करता है? वो चार्ज को एक्सेलरेट करता है ऐसे. अब एक्सेलरेटेड चार्ज गिव्स व्हाट? मैग्नेटिक फील्ड, राइट. वो फिर रिफ्लेक्ट होता है तो इलेक्ट्रिक फील्ड, यू गेट इलेक्ट्रोमैग्नेटिक रेडिएशन. अब वो चार्ज को ऐसे एक्सेलरेट करता है तो फिर अपनी पोलैरिटी चेंज कर लेता है एंटेना. तो चार्ज क्या करती है? अभी वो ऐसे गई थी, अब क्या करती है? वो पीछे की तरफ भागती है. तो यू गेट दिस electromagnetic radiation coming out from the antenna. What is this? Sound waves. Yeah. Now this is also a, अगर आप इसकी sound waves आपने स्टडी की थी जब ड्रॉ किया था उनका जो रेडिफिकेशन एंड कंप्रेशन साउंड वेव्स का. इफ यू ड्रॉ दैट आउट, यहाँ पे शायद आपको नहीं नजर आ रहा होगा लेकिन ये दिस इज आल्सो साइनोसॉइड. दी डेंस कितना वो कंप्रेस हो रहा है, कैसे रेडिफाई हो रहा है. कंप्रेस हो, अगर आप उसको ड्रॉ करेंगे तो दैट आल्सो कम्स आउट एज अ साइनोसॉइड. दिस कवर्स अ लॉट ऑफ द यूनिवर्स एक्चुअली. हाँ, तो दे आर देयर, सो व्हाई नॉट लुक फॉर देम. या ओके. It does something more general. It works with complex sinusoids. Again, you could ask why complex sinusoids. Yes, तो हमने वो पहले complex sinusoids हमने किए हुए हैं. But I will, we have looked at this before, so I will just skip it. What is complex sinusoid? But in general, the reason we go for complex sinusoid, it basically intuitively, mathematically it's here actually. It's more general. It covers everything. It covers cosine and sine as a subset. Yeah, complex sinusoid. क्योंकि उसका रियल पार्ट कोसाइन होता है, इमेजिनरी पार्ट साइन होता है. बट ऑल्सो दे आर मोर जनरल देन रियल साइनोसॉइड, दैट आई ऑलरेडी सेड. मोर एलिगेंट एनालिटिकली एंड इन कैलकुलेशंस. ओके, क्योंकि आपको कोसाइन ओमेगा टी प्लस साइन ओमेगा टी या मल्टीप्लाइड बाय साइन ओमेगा टी का इंटीग्रल लेना पड़े ना तो आप तो थोड़ा सा घूम जाएंगे आप, राइट. लेकिन इसी को अगर हम उसमें लिखेंगे ई जे ओमेगा टी तो प्लस ई माइनस जे ओमेगा टी प्लस कुछ इनमें आ जाएगा ये जब. so you can separate and solve, and these are very easy to work with because you know that the complex sinusoid is a eigen function of integration actually. तो वो खुद ही आता रहता है बार बार. things become easier. Yeah, so more elegant analytically doesn't mean you cannot do that. Okay, just cosine or sine say. That is called a cosine transform and the other is called a sine transform, where you don't write here this thing, you write cosine omega t or sine omega t, but again not heavily used. This guy is the major general thing. Yeah, so I think that is it. formula again we will cover it next time inshallah, we don't need to do that. And I don't know if you read XKCD comics, these are a like a prerequisite for being a nerd.
कॉमिक पढ़ने वाला को आया नहीं
तो वो एक ही बंदा था जो सब कुछ करता था या ये तो 3-4 हैं जो चुन के नहीं आए? अच्छा ठीक है, well पढ़ा करें कॉमिक्स हो यार, there's a lot of intellect in there बनाने वाले, right? So anyway, this is it. और कोई सवाल है तो बता दें, otherwise we are done.
सर ने अभी बताया